Yeah, I welcome you all to today's talk organized by the Center for Equitable Artificial Intelligence and Machine Learning Systems. My name is Blessing Ujeme. I am Assistant Professor in Computer Science. I will be moderating today's session. Seamless lecture series is an essential feature in Seamless goals. Today's talk is focused on fairness measurements, metrics for measuring fairness, and what residuals reveal. Today we are delighted to have Dr. Christan Grant, the Arnold and Lisa Goldberg Rising Star Associate Professor in the Department of Computer Science and Information Science and Engineering at the University of Florida. Dr. Grant directs the US Data Studio, a research group advancing new AI theory and systems for data that today's model struggles to process. His work spans fairness-aware learning under distribution shifts, natural language processing for encoded visual writing systems, and low-resource or atypical speech and interactive human-AI reasoning systems. Dr. Grant's research appears in many of the fields top venue, including knowledge discovery and data mining, International Conference on Data Engineering, Association for Computational Linguistics, and Empirical Methods in Natural Language Processing. And his recent work on audio large language models and child stuttering speech, and the Best Paper Award at the 2025 IEEE Automatic Speech Recognition and Understanding Workshop. Dr. Grant is also an active leader in the research community, serving on the Very Large Databases 2026 Review Board as an area chair for Knowledge Discovery and Data Mining 2026, and as a distinguished program committee member for International Conference on Data Engineering 2026. Dr. Grant's work is supported by several competitive funders, including NSF, Amazon, USDA, Federal Aviation Administration, Colgate, Family, and the Robert Wood Johnson Foundation, reflecting the broad impact and societal relevance of his research. Dr. Grant earned his PhD at the University of Florida as both an NSF Graduate Research Fellowship Program Fellow and NSF Lloyd Stokes Alliance for Minority Participation Bridge to Doctoral Fellowship. Please join me to welcome Dr. Christan Grant to Seamless Lecture Series. He will be speaking for 45 minutes and he will respond to the questions that you have posed during the presentation. Dr. Grant, the floor is yours.
Thank you for having me. It's very kind words. I know you've read my bio, but it's great meeting you. I know you and the stuff that's going on at Morgan State. We've been following it, and so I think I'm really happy to be able to talk to everyone, and hopefully I can make it there in person sometime soon. So let me share my screen, and Blessing, could you give me access?
I will. Yes. Yes, you can share your screen.
Okay. There we go. Share. Okay. Okay. All right. I hope you can see it. And
clearly. Thank you.
Wonderful. So today's talk is going to be fair by what measure? That's the title I gave it. And first, thank you for having me here. And so the work we're talking about now is under current development. So it's not really published yet. So I'm open to quite all questions. And please, it's fine, I think, to interrupt me or for clarification at any point. I'll keep my eye on the chat also, and I should be able to do that. Um, okay, so in today's talk, I'll just give an intro to me, a little bit more details, and I'll talk about this fairness idea and also this metric landscape that's proposed to help solve or alleviate this idea of fairness, especially with AI and machine learning. And then I'll point out why the metrics that are used individually, why they fail, and kind of maybe late in the talk, we'll see how time goes. I'll introduce this idea of RISE, a residual method of looking at fairness. All right. And then I'll give a little demo of the tool that my students used. And at any point in time, we'll have questions, but I'll leave some time also. All right, let's get started. All right, so the too long didn't read. So if you can only stop in, get a start of lunch and leave, the takeaway is that metrics that you use are diagnostic tools. They're not moral verdicts. So a single number, whatever the metric, it cannot capture the full picture of what's happening or the behavior of a model, of any type of model. And so residuals is what we propose. They help reveal some of the disparities and show what a lot of the single metrics miss. All right, so if you take that idea, don't trust the metric, don't trust the single metric, then I think you're good. This is a good takeaway. And yeah, so let me briefly introduce myself, Christan Grant. My students call me Dr. Grant, and I'm over the UF Data Studio. So I got my degrees at University of Florida, and where I was a bridge, that's supposed to be a bridge to doctorate fellow. And I also had an NSF graduate research fellowship during my time here. Then I left directly to the University of Oklahoma, where I was there about 7 years and got tenure. And in 2023, I came back to the University of Florida in the same department, the CISC department. And so things I go after, I'm happy to answer questions about, all this path as well. I think there may be some undergrads um, on the call as well. But the things I discovered that I like are looking at what's hidden. So trying to find things in data or patterns that aren't easily seen, right? The paradoxes. And then use the tools that I've learned in classes and to theorize why those things are hidden or why those items exist. And so this shows up in a bunch of different ways. So you can go to my homepage or UF Data Studio page and see some of the different projects that we work on. All right, so we have in a lab of 5 PhD students and a bunch of masters and undergraduates in the UF Data Studio, and the students are good. They're publishing. They're doing a lot of work, working really hard, and publishing in a bunch of different places. And my work has been funded by a bunch of different organizations that I'm very thankful for. So yeah, look up UF Data Studio. You can send messages, and we respond, especially the students. Um, Okay, so yeah, I want to send a picture of them. I don't know if they have the same picture. Some of them are on here. Um, we have, a couple students, we call them the cast. And if you go on the website, there's a supporting cast of MS and BS students and high school students also. And then we have some alumni who graduated and went to great places, and they're doing really well. Okay, all right. So let's jump into this idea of fairness. So everyone is pretty well equipped with this idea of fairness. So I'm going to walk through probably things, articles that you've probably seen. So if there is an important aspect that I'm skipping or missing out, feel free to add it. And I'm speaking to the choir on a lot of this. Okay. So first, the main point is classification is discrimination. All right. So every classifier has to draw a boundary and decide what class is what. So a model that distinguishes between cats and dogs, yes, that's some technical exercise. And a model that distinguishes between loan applicants is also a technical exercise. But if it's doing it by race and you look at the implications of your models, then there are stakes that are high that you shouldn't ignore. And so this is important to repeat and kind of hammer that as engineers, you have a moral responsibility for the algorithms that you're working on. Okay, and I don't know, it's important to note that I'm going to talk about fairness metrics, but this X or no is an option. So we're not constrained by AI-based metrics and or AI systems, but this talk is, you can assume that we're discussing discussing these metrics in in an environment where these are used already. Right. So if you have residual disparity that can't be closed, we'll talk about that later. It's okay to say to your manager or to the stakeholders, this model won't work. We can't use this. Same if the training data can't represent the affected population, you can say no. And if you see issues with and maybe a decision needs human context, you have to say so. So this is important to mention. So as you graduate and as you work on these problems, your expertise requires you to say no in a lot of different circumstances. And so fairness audit, where you're looking at code and an environment, if you cannot say no or this can't ship, then you're not really doing an audit. All right. So it may just be a fun exercise. So this is, with AI, and you have responsibility and you have power here. So it's important to be able to use the power where appropriate, ethically and morally. Okay, so let's look at some real world cases of these metrics and AI in the world. So the first one, I think, is super popular. This is in 2016, ProPublica looked at the Compass recidivism scores. That's how likely someone would reoffend. And they found that Black defendants who did not reoffend were labeled as high risk by the algorithm at roughly twice the rate as their white counterparts. So in the image, there's someone who has a risk of 10, risk of 3. And if you follow the article that's still on ProPublica, you can see which one actually did reoffend. And so this article in 2016 started helping scientists and researchers ask questions. Okay, should I trust these models that I'm deploying? Okay, another one is the gender shades work by Joy Buluini. So in this work, it found that commercial gender classifiers, 3 and then more later, had only 0.8% error on light-skinned men and 34% error on darker skinned women. All right, so a huge difference between between two sets or subgroups of people that were studied here. And so this work, the subsequent work, ended up in some changes, but this issue is still there. How do the models affect the people or subgroups inside of the data set? Okay, another one is a paper by Obermeyer in 2019, and they found that a commercial risk prediction algorithm that was used to judge how healthy someone is, essentially, there's a big disparity between Black patients and white patients, so that and the subsequent consequence of that is that it predicted healthcare costs and not needs for people. And there's a subsequent inequality between the groups of people. And this comes down to how do you measure the algorithm? So there's people, there's engineers, there's statisticians who are approaching this problem and need to consider, okay, how do I know that I'm not going to be one of these cases? Right. So what they all have in common is that the systems had fine overall accuracy. It was fine overall, but they failed on a significant group of people, significant, not just in number, but in the people too. Right. So if it failed in them, and so what was hiding it is some aggregate accuracy. Right. And so it wasn't the same as the overall group accuracy. Okay. And so when you have these models, you start encoding the bias, and that encoded bias comes from all over. Right. So when you first start collecting the data, there's representation gaps in the training data that you use. And some of those gaps or issues come from historical patterns that are baked into the true labels, right? And the measurement tools that you use to identify and calibrate majority and minority groups may not be calibrated equally or correctly. Right. And so when you're training, machine learning use these loss functions, and these loss functions help identify how close you are to finish, training, or how close the model is to finishing training. And it doesn't look at every error. Most of them don't look at every error in the same way. And maybe they shouldn't, but there's cases if you don't look at it, if you don't examine it, there could be consequences. Right. And a lot of times when you have a disparate amount of members, the overfitting that the model does will favor the majority distribution, the majority population of your training set. And then when you're labeling, so humans label, my students ask or have volunteers help them label data. And depending on the data set, each of those volunteers come with bias that may turn into a incorrect or impartial labeling of the data that's used downstream. Right? And finally, in deployment, once you deploy the model, the system that you built for and that you trained on may have a completely different distribution when it's out in the real world. Right? And so we can see an example of this on the next slide here, which which may or may not be intentional, but redlining maps or maps that identified different neighborhoods. Um, they shape even modern day housing, modern day funding, and modern day school districts. So the modern credit models that are used for these neighborhoods, they don't see race as a column. That's not used. It's illegal. But they see zip code, income, employment history, education, and probably others. And those features, those race features are still encoded into the map. Right. So the algorithm doesn't need to know race or any other protected attribute to be able to discriminate it. All right. And so that's the implication for the talk. So fairness can't be overhauled or fixed um, by looking at one number on a split data set. So you need tools, and people are developing tools that reveal, okay, what's the model actually doing across the populations with respect to fairness and performance? Okay. Okay, all right, so let's talk about this fairness metrics landscape. Um, all right, so hopefully you've seen the top confusion matrix before. All right, so this is what's the output of a classification model, a binary classification model. So you may have a predicted attribute, and here we say 1 or 0. And then you can check whether or not that attribute was actually 1 or actually 0. Right? And so we can create a matrix with those combinations to say true positive if you correctly predicted, yes, it's a 1, or a positive. You can have a true negative if you correctly predicted a 0, and the 0 was the truth in that context. And then there's false negative if the outcome was a 1 and you predicted 0, and false positive if the outcome was 0 and you predicted 1. So from this confusion matrix, you have these subsequent measures that you can use, like recall or sensitivity. And that is the true positive rate, or how many of the correct responses did your model or classifier find. You can also have false positive rates or false alarm rates. And that is how often did your model incorrectly say, yes, something is there. It's false alarm. Right? And then there's precision. This is how when your model predicted something positive, like say the true positive, how likely was it correct, or how often was it correct when it predicted something positive? There's this notion of base rate to say when you have a true positive or true negative or a false negative, how often do you predict that? What's the prevalence of that over the whole model? Right. And so that's called the base rate. And then we use, in general, people say accuracy. And we say accuracy and we mean a lot of different things, but accuracy is really just the true positives and true negatives over everything. When we're looking at metrics, accuracy is just one of these metrics. And it's the one metric that can come from this type of confusion matrix. And then there's lots of derivatives from that, where you can take the geometric mean of the precision and the recall, and you can create graphs and find the area of them, and there's tons of others. All right, these are the traditional metrics that are used. Now, there's also several fairness metrics in literature. There's hundreds of them. So here are some of the popular ones, and I want to point out the families of them. So there's tons of them, but there's different families of them, and maybe in the next couple slides, I'll step through what some of these fairness metrics are. And I should note that each of these fairness metrics say something. They describe the data set in some way. And there's multiple fairness metrics because there's multiple ways of saying something is fair or not. Right? And each of the metrics, whatever your decision is, the metric that you choose, you may have a different actual outcome, and you may hide something from your data set or from your user if you only look at one of the metrics. Okay. Okay. All right. So let's look at three of the families. Pause for a second. Okay, so yeah, there's three families of these fairness metrics: independence, separation, and sufficiency. So please ask questions here. I want you to get at least a notion of what these mean. So first is demographic parity. This is an example of one of the independence metrics. And you can think of the independence metrics as both of the metrics are measured kind of separate from each other. And fairness means some type of equally positive rate between those two separately measured metrics. So in this math equation here, or this expression, says that the probability of the model predicting yes or positive for one attribute A, is the same as the model predicting positive for attribute B. So if they both have the same rates of saying positive, then you can say you have demographic parity. All right, that's the independence one. So next is the separation family, an example that is equalized odds. So in equalized odds, you want to look at the model's prediction with respect to the true outcome. Right, so you may ignore in demographic parity, we don't care if it got this prediction wrong or not. We're just looking at the prediction. So here we want to say, okay, what's the prediction? How often does P, or the probability P predicts positive, given a certain true value, a certain true value, or a gold label? And given that, how does that compare to the same thing with group B? And so if we're just looking at the true positive rates or false positive rates, if you flip it across the two groups, that's what we call separation, or we have the odds that they're selected and they're selected correctly are the same. And so that could be another notion of fairness. And then next is sufficiency. And sufficiency is predictive. One of the examples is predictive parity. So it's instead of looking at what's predicted, we want to look at, okay, given this true value, how often does the model predict yes? Right. And so we're still looking at the two models, but we look at it from the aspect of was it correct or not? And so we can say this is like the equal precision across two different groups. Right. So they're slightly different. And you have to regularly look at the definition to remember what it is. But each family of these encodes some type of moral intuition. Like if you're a stakeholder, if you're building a model and you're looking for fairness, you have to choose one of these um, and and follow up with that downstream. All right, let me give you one more example. So this is a ratio example of the independence. This is disparate impact, where we look at the probability of yes of an unprivileged group divided by the probability of yes for a privileged group. So here's a quick example of how you calculate something like this. So let's say we had 100 applicants for a job, and the classifier says yes to 60 of them from group A, and 45 where group A is the unprivileged group, and 45 of them from group B, where group B is the unprivileged group. So that would give us a ratio of 0.75. Right. And so this disparate impact was used in uh, in a court case in 1971. And this is where one of the four-fifths thresholds or legal standards were given for disparate impact. So how much can you be below four-fifths disparate impact between different groups? This is what is used, and can be used in other situations, but it's not enough, right? So if DI, this value, 0.75, says nothing about whether the 5 accepted from group B were the right 45. Why did we select those 45? Or did they end up being good? Right? It says nothing about, there's no true positive value in here. Right? It treats both of these selections as equal when maybe they're not. And when you deploy these models or use them in practice, usually there's some threshold to say, yes, this model is good or bad, but even moving this threshold can flip the disparate impact value. And this is another key point, meaning that the fairness metric that you're using is unstable. Like, how do you trust it when you have different models? It may give you different values. Okay. All right. So we talked about these fairness metrics, and I'm positing that they can be misleading. One of the reasons is they can't coexist well, and they may drift with the threshold that you choose, and they hide variance or randomness. All right, let's look at some examples of that. One of the main ones was the impossibility theorem by Kleinberg et al. In 2016. What they said is that metrics from these three families, if you try to optimize for all of them and say, hey, we have a model, we know our three different metric family groups, let's just build a model that says, all right, we're gonna have the best demographic parity, best predictive parity, and best equalized odds, like the maximum optimal versions. What they showed is that outside of some kind of degenerate random cases, no classifier can satisfy all three of them. So what that means is that you basically have to choose, right? And so choosing the metric is a value judgment. So something's going to suffer because of your choice. It's not just technical, right? You have to know about the downstream cost of that. And so depending on the situation, you may have different stakeholders preferring different metrics. And a tool that just looks at one is difficult. So here's another example. I'll go through a little quicker. So if you change the threshold to your model, it may look fine, but if on certain, maybe at the ends of your threshold decision boundary, it may have the metric value may change. And so you can't depend on thresholds when you have models. So in this example, I'm showing that if you go from 0.8 to 0.9, and the metric values change. And these are two equalized odds and demographic parity values. All right, so these metrics are threshold dependent. All right. And let me move a little faster. That's what we're saying here. All right, so also, if you have a model, if you look at this graph on the left, so here is the predicted probability of a group in green, group 0, and a group in kind of red or lighter pink. What you can see is they both kind of have the same curve. They have the same median, but the variance or the spread is different. So green stops around here, while red is spread a little bit more. So what that means is if you are trying to predict for one group, you may have more randomness or more random selections in that group if you don't consider the variance. Right? So if you're only considering the mean or one part, you're missing a big part of the model and the model's prediction. All right, I'm going to speed up a little bit here. All right, so we looked at some of the pros and looked at some of the single metrics and rushed through a little bit. Please stop and ask questions if you don't believe me or if you want me to give some examples. But these metrics are great. I mean, they're easy to report. You can calculate them. There's great libraries for them. There's historical precedent for using some of those thresholds and metrics. And it's easy to optimize when you optimize one, single metric, and you can compare these metrics across different models. So the cons are it hides the variance. They may have some weird behavior of the model that comes from the data, and it depends on these thresholds of where you set the boundaries of the decision boundaries of your model. And the impossibility theorem is a feature, not a bug. It's encoded in there. It's not something you can beat. And so these metrics conflict with each other in ways that may not be clear right away. But it also hides the harms to the subgroups. So you get this false sense of security saying that, oh, this is great, but there's still these aggregated harms when you're using these single metric models. Okay, all right. So this is where we introduce RISE. Yeah, so RISE, I'll explain what RISE is, but let me give a little bit of background. This work, actually, I didn't include in that slide. This is part of NSF, Amazon grant. And we're looking at these different metrics, and we were looking for one metric to solve everything. And we found out, like I said before, that's not the case. Right? This is why we're doing some of this motivation. So instead, what we want is we want a metric where we can at least characterize what's happening with fairness and then extract principles from it. And we'll walk through RISE and I'll show you how it works. And I can load up the demo page. And if you have questions here, this is where you ask, because this is brand new stuff and where this work is under submission too. Okay. So the core idea is this. So you get some data, you get the predictions, and you get the attributes. And you have a function that predicts, for simplicity, binary true or false, yes or no. All right. And what you can do is you can create the residual. The residual, if you've taken stats or in data science, especially with R, I feel I've seen sometimes data science and Python skips this idea of residuals. It's basically just the error. It's the error between the predicted value and your actual value. So that's what this P is. P hat means we predicted it and minus the actual value. So the signed error. So if we get this value, and I'm going to show you a little bit of Python code, because it's very simple. If we can, over the whole data set, subtract our predictions minus the actual value, then we can sort sort the residuals. And when we sort them, we can plot it. And we get this plot that characterizes really the accuracy, but encoded in that is also some what we think are some links to different fairness metrics, right? And we can do this for each group independently. Let me so the residual value is greater than 1 if the model overpredicts. So if we predict 1 and the actual value is 0, you get something greater than 1, and you predict less than 1 if it underpredicts, and so on. And note that I'm gonna stick with the classification example, but this is easy for residuals or for continuous values. Like if you want to predict a range or a probability, this residual idea still works there. Okay. All right. So the building blocks to this are these F metrics. And so these F metrics describe what's happening in the model. So okay, so to make sure you see this, I'm going to show you these metrics. I'm going to show you the visualization and then jump back to the definition of the metrics, because I want to leave some time for questions. So I have let me see where I should jump to. 1 second. Oops. Okay. All right. So we'll come back to this metric idea. But what we're doing is we're going to have a curve. I'll show you the curve. And the F metrics are just kind of values that come from that residual curve. Okay, we can come back to that. Okay, so this is what the curve looks like, or two examples. So there's one on the left, one on the right. So the one on the left is a well-calibrated model. That means it's a good model that performs well over the data set that called civil comments, the data set that it was trained over. And so we calculated the residuals, sorted it, and plotted it. And so when we sort it and plot it, you can see it has this natural increase. So all the bad residuals, or the not bad, let's say the negative residuals are on this side. And then as you go up, there's a lot of residuals that are about zero. That means there's a lot of good performing values. And then at the end, you have some of the over predictions here, where it's where D is greater than zero. Right? And so what we get is this characteristic curve. Right? And this curve can tell us a lot. And so we examine the curve. What we're trying to discover now, we have some, we can ask questions for details on it, but I'm going to be a little bit high level here. And so there's parts of the curve that we can identify that have some characteristics. So first, this knee point. So this knee point, left knee point and right knee point, think of this like like the derivative of the curve here. And so right here is where the sharp curve, in data mining, if you've done the knee or elbow plots, this is what a knee point is. This is where is there a big jump in the curve. Right? And so these points we think will show or hide something of the model. So why is the model just starting to perform very bad at these points? And we think we can identify this at the knee points. All right, so this is a well-calibrated model. So both residuals for each group are very close together. All right, so this model isn't as good. And so we know it's not as good because we can see these spaces in between them. So we have a group 0 and group 1. Group 0 is green. Here, there's the residual curve, and group 1 is red. And what we see in between are the differences or the gaps between the performance of those models. Right? And so if we separate this RDF curve into the groups, the gaps in performance here tell us a lot about the type of disparities that's happening between the two different groups. I should mention that between here, the x-axis, this is the percentile. So if there's one group is larger than the other, we still sorted by just the percentile. So we fit the sorted values inside of this group. Right. And so this space here, this gap here, we can calculate that area using the Wasserstein distance. Basically, if you remember calculus, maybe Calc 3, it's how you fill this curve, how you fill, if you take a shovel and try to fill the area, this is what's happening here. So we can compute this value here, and we call that the F distance, or the distance between the two measures. So a curve that's really good or really close between the two groups, where they perform similarly, it's going to have a very small F-dis. If there's a large gap, there's something happening. There's different character. Both the groups have some different characteristics. Okay. Okay. We're running out a little bit of time. But yeah, so the shaded area is the Wasserstein 1 distance. And there's other attributes that I skipped before. So we can look at where that knee curve is. We can look at the median of both values and see the distance of those medians. And that's what we call the pattern. So if one value is shifted over to the right, then and the other shifted to the left, there's a gap between them. Then that means that's one type of difference between the two groups. And we have FH and FV, and these are basically where the sharpness or the change of the curve. So FH is where the knee points are for each group, and you can subtract it and just get the distance between both of them. And so if one horizontal curve is higher than the other, that may mean it has worse performance at that point. And kind of same thing with vertical. And so what we end up seeing is we get these we call them F metrics. This curve I'll show you a couple lines of code, is pretty simple to create. We get a value that's showing us the characteristic of a model on a data set. And then, so given that, we can export the diagnostic or the model to the stakeholder. And then, okay, so also given that, we can show which group carries the disparity pretty easily. So if we take that distance, we can look at the distance of where 0 is positive and where 1 is positive, and that ends up being the F-dist. But we can look at the group 0 and group 1, and depending on which is which, we can tell which group is is having poor performance in their model. We can compare the performance between the different groups. And we also have something called rho. That's a ratio. If we say group 0 over the whole disk, it will tell us if it's about 1, that means group 0 is systematically overpredicted. And 1 would be when the F-disk here is the same as this F-disk. If it's about 0, then group 1 is going to be systematically overpredicted. Right, and if it's half, that means the quantile curves cross, and there's disadvantages happening at different parts of the distribution. And and what we see, I'll speak through this quickly. This method is also threshold invariant because we look at examples, and we're looking at metrics or reading metrics over the full set. We don't have to worry about the thresholds changing. We're looking at the raw performance. And so that's another win. All right, so let me show you. Let me see if did this update? Hold on, it didn't update yet. I think that's okay. And so I have two examples. One is so I should mention, pardon my dust, right? We're still going through this stuff. We have two demos I'll show. And let me know if you can see this still. It's a Streamlit dashboard, and I'll show this one first. Yeah, I'll show this one first. And so we can upload our own data set with the predictions and then maybe with other F metrics here. But there's a preloaded one. This is the adult data set. And we can see the characteristic of this curve. What this shows is, hey, there's a big disparity of the positive residuals, right? So there's something happening there, right? And so here there's old metrics we can get, like accuracy, mean difference. These are other we say old metrics, but the current metrics that people use, they're here, but we also have the rise metrics here, and we can show that, hey, this is pretty poor. And here we have F-disk good, but that's it's actually a little error in there. Okay, and so we can locate the knee points and color different places. We can also look at environments or kind of secondary variables and see how the model performs or the curve performs when we look at look at the results inside of a secondary variable, like an environment or context. And I quickly want to show you the other one. So the other one, I won't put some of the examples, but it is this examples is from the hate speech and toxicity data set. And yeah, I won't show the examples, but it's hate speech. It's actually hate speech. And so I don't want to show too much of that. But what we're doing here is we're looking at text data, and we allow an auditor or someone to say, okay, where I see all the points here, let me go and search an example and see where this example is. And so what we're using this for is to say, can we look at the knee points? Do the knee points, like right here, is there something special about the data points around these curve that make it so that this curve or the curve down here that make it so that they're the last ones before the errors get really bad? All right, because again, the residuals, we want them all really close to 0. And a couple other things. So we can show the lines, these 0 lines, these are the median lines. And these median lines will be the difference, like the F pattern would be the difference between the two median lines. Okay. Yeah, I can show a little more, but let me continue on this. That looks okay. There's better. Um, Sure, yeah, you can see that on our website. So this is kind of an example output. I just showed you one. There's another example here where instead of showing the two lines, we sort both groups and then we color the groups that have, we look at every some number, every 50 or so um, values, and we color the values, we color the segment of that line with the winning attribute. Actually, I can just show you here. I think I have it. Um, Segmented residual curve. Okay, so here there's a couple groups, or there's two groups. There are the blue and yellow sensitive attributes. And so they're both sorted together. So what you see here is in the middle, and the middle is usually around 0. You see blue is performing well here. Blue, the 0 sensitive attributes. And since we see yellow at the ends, what that's saying is that yellow is probably has the worst performance because they have the highest residuals. Right. And so this can tell us the difference between the different groups just in the visualization. Okay, 46. Okay, so there's a little bit more in there. And I'm showing you in text. So okay, so what's next? What are we working on now? So we see the evidence here. We have a setup, we have different scenarios that we looked at. What we're trying to do now is look at the principles that are shown. Look at different data sets and say, hey, if I see this type of curve, what does that mean? Or can we predict? Can we say, hey, this curve means you have this type of fairness or bias in the data set? And can we match between the two? Or can we use that to help either direct auditors or help changes or updates to the data? Um, Yes, we played in a bunch of different data sets, and I think I'll stop there. And I want to leave a couple takeaways. The first one is that classification is discrimination. That's those words in machine learning are synonymous, but it's what you have to, especially computer scientists, have to say whether or not that discrimination is justifiable, is it observable, and is it accountable? And can you measure that? Next, every metric, fairness metric, is a value judgment because they can't use them all. And should mention, well, let's keep going. So single metrics lie by omission because there's things that are missing out. You may want to, and some people do, look at several different fairness metrics, and after you run your model, go check all those different fairness metrics and try and get them all within some threshold. But we think that residuals are richer objects, right? So if you, from that plot, you can get um, these type of F measures. There's a couple more. And we have to know, the calibration, can it be trusted? Yes or no? And what tools can you use to do that? And you should build diagnostics, not just dashboards showing data, but people should be able to interact with the data. And I will stop there. And yeah, thank you for your time. Thanks for listening. Please let me know if you have questions.
Thank you so much, Dr. Grant. That was a great presentation. Thank you, Dr. Grant. That was great presentation. Yeah, I can see a couple of hands up for questions. Yeah,
Yes,
yeah.
I see.
Philip?
Sure. Hey, thank you so much. What an impressive presentation. I mean, I've done a little bit of work on this stuff, and your coverage of it is just so detailed and masterful, and you make it look easy when it's not. And so thank you so much for joining us.
Thanks.
Um, I wondered about if you could, so this is sort of a clarificatory question. If you could just say again kind of what the residuals idea is, what the residuals are measuring. I'm sort of understanding it as like divergence from correct prediction per data point. And maybe I'm misunderstanding that. But and then if you could talk a little bit, I mean, I know you already did this, but if you could just say kind of like in a nutshell what each of those F scores is measuring and sort of why that's something that we care about in this kind of context.
Yeah, sure. I'm happy to. So first, let me go back to a good definition here. Right. So this is a post hoc analysis. So when you already have the data, maybe it could be training data, and you want to compare that with your model's prediction, right? It could be real world stuff, but you're comparing it. And what you do is you compare each point, the prediction for each point with your prediction, right? And that's the residual. And so all we do is we sort those residual values and we get a curve from it. All right. And so after we've done that, the part that we're still working on now is saying, okay, what does this curve mean? We know it means something. We see the difference in performance, but what are the principles behind this point? And let me see where I think I had some slides with each of these points. I'll start with this one. I don't remember if it's this one or not, but these are the metrics that in the paper, we kind of say why these are important in a little detail, but let me just discuss each of them. So these are features that you can extract from the visualization. Yeah, before I talk about the details, I want to say I think the visualization is really good, and you can get. I was telling my student today, Ray, who's working on this primarily, that hey, if we just find principles or examples of curves that have certain characteristics, we can just look at that and describe something or say something about what's happening with the classifier and the data. But from that, if we need a number, we extract these types of numbers. So first, the PAT, or the position alignment, is the median. It's the average of the medians between each of the groups. Right. So we have the curves, and the distance between those two groups, that's the FPAT. And so if they're the same, if the medians are the same, that says something about the model, maybe says that they're similar. If they're very far, there's some disparity going on in there. So I mentioned FDist already. That's kind of the area between the two curves. And the FH and FV are the horizontal gaps. Let me see if I can show it here. It's very small, but hmm, I don't think let me look at this one. Do we have the FH here? Well, in any case, so the FH and FV are, H is horizontal, and so we try and identify the location of the the knee point, which is just like just where the curve starts. We don't have a stronger definition than what the knee point is, but we would put a line through there, and we can put a line through the other knee point. So there's a blue knee point and there's a yellow knee point that you can't really see. Maybe I'll zoom in here. Let's see. It should be a yellow knee point. I think they're pretty close. So if we look at the separation between those knee points and the ones on the other side and average them, and then that tells us, okay, how sharply or how quickly does this model kind of go bad. All right, let me go back here. All right, so we do that kind of vertically and horizontally. And I think maybe I didn't. We have some other measures that we're trying to understand and trying to find out. But maybe if there's other questions, I'll mention that. Yeah, we thought the knee point is where all the worst stuff are, where the confusing data points are, but that's been hard to define. There's evidence that like if you sort all the points that corresponded to the knee point may be weird, but we don't know how to characterize it yet. Thanks for the question.
Thank you.
Any other question? Where do we sign in? Sign into where?
I can ask just one more question about the x-axis in these graphs. What is that, if you don't mind? What's the x and
Yeah,
y on
sure.
the graphs?
So the Y is the residual. Let me go back here. And the X, I didn't clarify it completely, but there's sorry, let me just show it to you here. There's two types of X-axes. Most of the ones you've seen, I think all of them are the percentile of those residuals. So once you have the residuals, you order them by their value. So the largest ones will be last, and the smallest ones will be here, and it's just ordered, and then we say percentile because we fit them inside of this range 1 to 100. But the value, so there may be a lot of small ones and a lot of large ones, but we put them within this range. And there's also where we just count them. We just we didn't fit them in a range. Sometimes we just put them between, just line them up, N0 to whatever the size of the data set was. And the y-axis is the residual value.
Thank you. Any other question? Yeah, no other question. Thank you so much, Dr. Grant. That was a great presentation, and it's quite engaging. If
Thank you for having me.
Yes, go ahead.
Oh, I was saying thank you for having me.
Oh, thank
I wanted
you.
to
Thank
put
you
up
so much. That was
our
great.
slides. Yeah. Awesome.
Yeah, so if you have any question regarding this presentation, you can feel free to reach out to Dr. Grant. He'll be happy to respond to you.
Awesome.
Thank you so much, everyone, for coming. I appreciate you all.
All right. Thanks, everyone. Have a good day. And
Dr.
thanks again,
Grant, we're
Leslie.
so happy to have you. Thank you.
Thanks so much, Dr. Grant. Extremely informative.
Thank you. Bye.
Thank you.